Dear students, welcome to PHY467. आज हम पढ़ेंगे Planck's radiation law and blackbody radiation. So, to know about blackbody radiation and Planck's radiation law, we should understand about thermal radiations. What are thermal radiations? So, anything that heats up emits radiation. So, for example, if we heat iron, it glows. If you see here, so there is a rod of iron that has been heated up and it's showing some kind of radiation. Actually, it initially when we start heating it, it is in red color. Then it becomes orange, and if we heat it even further, it becomes bright yellow, and it gives off bright yellow radiation. These are called thermal radiations, and Planck's law actually is all about study of these kinds of radiations. But I will tell you a little bit about the history of these radiations. So, Kirchhoff, the famous Kirchhoff for his circuit laws, Kirchhoff voltage law and Kirchhoff current law, he actually noticed this kind of there is a connection between the emission spectrum of material and the absorption material of a material. He saw that the emissive power of a body, emissive power of a radiating body is related to its absorption power. He was the first person to notice this phenomenon. So, what that means? He saw that when we heat a gas or some other material, it gives us an emission spectrum. It emits some kind of radiation that we plot or we put on a screen. We get this kind of spectrum. And he also noticed that if we have a hot source, and if this source is bombarded onto a cold gas, I mean, if we bombard radiations on a colder gas, so some radiations are absorbed and we get an absorption spectrum, and the lines, they actually match on this frequency spectrum. The emission spectrum and absorption spectrum, they have same kind of emission lines and absorption lines at the same frequency values. So he was the first person to notice this kind of thing, and he said that this is not a sheer coincidence that these absorption and emission lines coincide, and he said that there is a natural law behind that, and for that natural law he imagined a kind of closed cavity. So he did a kind of thought experiment. So Kirchhoff, to be precise, he did a thought experiment in which he imagined a transparent closed cavity in thermal equilibrium, and since it is in thermal equilibrium, the amount of heat absorbed is equal to the amount of heat released, so there is no heat transfer. And what that means, it means that the all the radiation that it can absorb, it can also emit. So all the radiation it can absorb, it has the ability to re-emit all those radiations. So this is actually really fascinating prospect. And Blackbody is basically kind of it's analogous to this. Okay, so first I mentioned that these kinds of radiations were called cavity radiation. So cavity radiations. So there is a full section about Kirchhoff radiation in our book that we are following, and I highly encourage you to read about that, and also search internet if you want to study in more detail. So the thing is, this Blackbody radiation, or Blackbody itself. So let's have some kind of definition what Blackbody is. So Blackbody is something similar to the cavity that that was imagined by Kirchhoff. So Blackbody is, this is something, I would say it is something imaginary or fictional. So something which can absorb all the radiation falling on it. So every kind of radiation with every kind of frequency. So this Blackbody, that is kind of a fictional or imaginary thing. So an ideal Blackbody is something which can absorb all the radiations. In actual, there are no such perfect objects. However, we have some close to perfect systems for Blackbody. For example, there is a material known as Venta carbon, or this is a kind of artificial material which was made with the help of carbon nanotubes, like this array of carbon nanotubes which can absorb all the light which can fall on it. Or we can treat our sun. Sun can also be treated as a Blackbody. So you will be wondering that how is it a Blackbody when it's a glowing object. So the problem is that this does not depend that whether it's glowing or not glowing. The definition is that it can absorb all the radiations falling on it. So for that reason, whichever radiation you can throw out towards sun, it will absorb, and later it can re-emit some radiation similar to that, similar to what it absorbed, and some other radiations. So it can emit radiation, thermal radiation, the whole spectrum of the electromagnetic rays, or whatever you say. The thing is, even this hot glowing iron can also be treated as a Blackbody material, because it can absorb as well as it can emit a wide range of thermal radiations. However, we have to consider that what that entails, what that means, why we study such materials, or such kind of why we make such kind of idealistic approach in thermal radiation absorption and emission. So to do that, to learn about its significance, so let's consider an ideal kind of black body. So we have a cavity, as I am showing you in this figure. So we have a cavity, like a hollow cavity of some metal, and there is a small hole in that in one on one of the sides. We don't call it sides, but okay, we have one hole in it, and the walls of this cavity are painted with some black material, black paint or black carbon. So whatever light enters into this body, so it reflects back and forth inside it. So there is hardly any chance that it will escape from this cavity. So this is our ideal system for studying this black body radiation. And there were some experiments in which these kinds of black bodies were created, and then the spectrum of these radiations was collected. So let's consider the some emissions spectrums of different black bodies. So here I have shown you 3 different emission spectrums. So this first one is black body radiation or emission spectrum of a blue star. This is the middle one is of a yellow star, and you see they have different kind of temperatures associated with their colors. So this has 18,000 Kelvin, this has 6,000 Kelvin, and this is 4,000 Kelvin approximately. So if you see that these spectra, they are between wavelength and the emitted energy of those black bodies. So you see that there is a peak in this spectrum. This is actually the black body spectrum. The black body spectrum of almost every different black body looks similar to this. There is a peak in between, and there is a decrease after that. So what I want to say here, that the peak is dependent on the wavelength and on the temperature. So if we lower the temperature, this peak shifts to higher wavelengths, and also the height of this peak also decreases. For more number of temperatures, okay, you can, for more clarity, you can see this spectrum of a different system set of black bodies. So at 5500 Kelvin it was a high peak, and at 3500 Kelvin the peak is very small, and in between it gradually decreases. And the first person who noticed this thing was Wien. So Wien presented his Wien displacement law, which says that the statement of this law is that the black body radiation curve for different temperatures will peak at different wavelengths, that is inversely proportional to the temperature. So if we want to write this Wien's displacement law, so it is like the peak wavelength, lambda peak, is equal to P over T peak. B is some constant. And at that point of time, when these spectra of black body spectra were observed, so the problem was this spectra looked similar to what we had in the case of our Maxwell-Boltzmann velocity distribution. You remember we studied this in some one of the previous chapters. There was a complete chapter of Maxwell-Boltzmann velocity distribution. And the people around that time thought that if this Blackbody spectrum looks similar to Maxwell-Boltzmann velocity distribution, then we can somehow deduce the thermodynamics from this spectrum in the same way as we did for Maxwell-Boltzmann velocity distribution. But that was wrong. What happened to that treatment? I show you one by one, not in detail, but somehow in brief way. So the first classical law that tried to explain this black body radiation was Rayleigh-Jean's law, and Rayleigh-Jean's law was can be written as B lambda of t equals to C kBt over lambda 4, which basically shows that the area under these curves under any of these curves is proportional to the inverse of fourth power of the wavelength of the radiation. Okay, so this is the area under the curve and this is the wavelength, and this law was at higher wavelengths. So I show you, if you apply this law at higher wavelengths, this black curve is the Rayleigh-Jean's law that tried to explain this whole curve. This is the experimental curve, blue one and green one and the red one, and he tried to, or they tried to explain, and at higher wavelengths you see they somehow get close to the experimental observations, but as soon as the wavelength is decreased, this law is far off from the experimental curve, and this disagreement actually shows that all the radiated wavelength is at lower frequencies, and there is no power that can be emitted at higher frequency, larger smaller wavelengths or higher frequencies. So this is a problem, and this is called ultraviolet catastrophe or Rayleigh-Jean's catastrophe. You can read about it in literature. I write its name. It is called ultraviolet catastrophe or Rayleigh-Jean's catastrophe. So it shows that if we plot in terms of frequency, this is now the same spectrum. Here it was between wavelength and spectral radiance, and here it is between frequency and spectral radiance. So it shows that all the power is emitted at lower frequencies. Here it shows that all the power is radiated at lower wavelengths. So this is known as ultraviolet catastrophe. So the first explanation, for the classical explanation, I would say, for the black body radiation was the Rayleigh-Jean's law. So Rayleigh-Jean's law can be written as B lambda t equals to C kBt over lambda 4. So basically it shows that the spectral radiance, the spectral power radiated by a black body is proportional to the 1 over lambda 4. And this law looks fancy, but if we look at its agreement with the experiment, so this is a plot between this blue, green these are the experimental curves, and this black curve is the Rayleigh-Jean's law for this blue curve. So you see at higher wavelengths it is somehow in good agreement with the experiment, but as soon as we decrease the wavelength, it diverges from the experimental curve. So it is totally catastrophic here. It does not show any agreement with the experiment at lower wavelengths. So this agreement is known as ultraviolet catastrophe or Rayleigh-Jean's catastrophe. So you can read about it in literature. I have written the word for that, ultraviolet catastrophe or Rayleigh-Jean's catastrophe. So there is a disagreement between Rayleigh-Jean's law and the experimental curve at smaller wavelengths. and there is this Wien's law that I explained earlier, that is lambda is proportional to V over T. This Wien's law is also not perfect, so this law actually explains this curve pretty well at higher frequencies at lower wavelengths, but at if you consider this curve, so at lower wavelengths or higher frequencies, this goes also kind of out of the agreement with the experiment. So this blue line is experiment, and this pink dashed line is the Wien's law. So both the classical laws, which were based on classical statistical physics, were somehow inefficient to explain the actual blackbody radiation curve. So there was a requirement of a new law, like a new innovative kind of scheme that could explain this blackbody radiation curve. So Planck came forward and he actually tried to describe this in terms of quantum mechanical model, and he introduced his own distribution function, and he could really well explain all of these this blackbody radiation curve in whole frequency range or whole wavelength range. So the theoretical Planck's law is actually if there would be some experimental points, they would lie exactly on this blue line, which is our Planck's law. So there is a total agreement between theory and experiment at lower or higher or middle, whatever frequencies we need to choose. So in the forthcoming discussion, I will discuss how we can reach the Planck distribution function from our statistical analysis, and we will see later why it happened that the both previous laws were insufficient to explain blackbody radiation curve. So let's start. So to understand Planck's radiation law, we need to understand some basic terminology. This terminology will be used frequently later on. So first thing we need to know is what a mode is, a mode of vibration or a mode of oscillation is. So mode of oscillation can be defined as a particular oscillation amplitude pattern. In simple words, it is a particular oscillation amplitude pattern. So if you remember waves on a string, so if we had a string and we try to produce waves in it, so if we pluck it, and it can vibrate or oscillate in different kinds of vibration patterns. So one of these patterns was like that. This was called fundamental mode of vibration. So in this terminology which we want to study now, we will call this a mode. So this was called first harmonic. If our string used to oscillate like this, if we somehow disturbed it from the middle, so this was our fundamental mode or first harmonic in case of a string. First harmonic or fundamental mode. It could also happen that if we increase the frequency, the same string, and if we increase the frequency, it could also oscillate like this. So this is the this is another mode of oscillation. This we used to call in case of string, this was a second harmonic. So this is another mode. So this is one kind of mode, this is second kind of a mode, and if we keep on increasing frequency, so at some frequency we would reach third harmonic of our string system. So third harmonic looked like, so we had here more number of nodes and antinodes. So here we had four nodes and three antinodes. So this is the third harmonic, and we will call this another mode, MODE mode. So first thing we need to know about this cavity radiations is that a cavity radiation contains, or a cavity contains, I would say, cavity that we are treating as a black body contains an infinite modes. So there is no limit how many modes of radiation can a cavity contain. So it can be millions of modes inside that. So because it can absorb all kind of radiations in it, so that it can be we cannot quantify this kind of thing. And the other thing we need to know that each mode contains fixed number of photons associated with it. That was the basic of the theory of which Planck relied on to explain this thing. So he said that if we have, okay, inside a mode we have several levels. This is our S is equal to 0, S is equal to 1, S is equal to 2, S is equal to 3, and S is equal to 4. So this is one, actually this whole thing is one mode. I just encircle it so that you should know. This is one mode, and one mode can contain any number of photons from 0 to infinity, and the energy of each mode can be written as n times sorry, I should use another symbol here. So S times h cut omega, where S is can be 0, 1, 2, 3, 4 up to infinite number. So what it shows that in one mode the energy is quantized in the units of, so I write it, in any mode the energy is quantized in the units of h cut omega. So the previous theories, this Wien's law or Rayleigh-Jean's law, were not based on this kind of thing. So they said every mode has an equal energy that is proportional to KBT, classical equipartition theorem. So when Planck came, he said no, it cannot happen like that. So each mode has a specific frequency, that is this omega, and each mode has a certain number of photons in it, and we don't know how many number of photons, but okay, if they have several photons, so each photon would have energy in units of h cut omega. So if we have 4 photons in one mode, for example of this kind, of this kind, of this kind, whatever frequency, so each photon will have energy in the multiple of h cut omega. So that was the differentiating behavior of Planck's law that was not present in previous theories. And this is from this law he could explain that how this thermal radiation can be explained in the form of Blackbody radiation law. So, and we don't know how many number of photons one mode contain, but okay, if we have 3000, if it has an energy 3000 h cut omega, so there will be that number of photons in that. So the presence of photons is really important. The quanta of energy is really important in this theory. So let's move forward. For doing statistical analysis, we need a partition function. So partition function is like a really easy thing to do here. So in case of the partition function for one mode can be written as z equals s starting from 0 to infinity e to the power minus s h cut omega, or minus s beta h cut omega, where beta is 1 over kBt. This is our standard partition function, because we don't have a limit on how many number of s or how many number of photons we can place in it. So the sum will start from 0 to infinity. And we have done this thing before, that if we have some quantity like this, if we have a sum like this, x to the power s, then this sum can be written as 1 over 1 minus x, provided with a condition that x is way smaller than 1. So in our case, x is e to the power minus beta h cut omega. So we can easily see that this beta h cut omega minus e to the power minus beta h cut omega is much smaller than 1. So our partition function can be written as 1 over 1 minus beta h cut omega. So we call this our equation. So I numbered from beginning, so the partition function here I call it 1, this partition function, and now I call this, after summation we call this equation 2. And now we calculate the probability of the system to be in this mode. The probability of the cavity to be in mode S will be Ps. That is very simple. We have done this thing many number of times. So that would be e to the power minus s beta h cut omega divided by the partition function. That is our equation 3. And in that state we can calculate the average number of photons that would be S average, that would be S times the probability, sum over all number of photons, and we can write it as 1 over z as from 0 to infinity s e to the power minus s cut omega beta. This is our equation 4. So let's do a change of variables in equation 4. Let beta h cut omega is equal to y. Then this term, this thing, summation term, we can rewrite it as s equals 0 to infinity s e to the power minus sy after this replacement, and this can be written in the form of a derivative d over dy e to the power minus sy. And now if we put the value of this summation from our equation 2, so we can write it as minus d over dy 1 over 1 e to the power minus y. This is from 2. I write the guidelines side by side. So this will be, if we take now the derivative, so we are left with e to the power minus y divided by 1 minus e to the power minus y whole square. So now we can put this summation term back in 4. So we will get, so our equation 4 implies that s equals e to the power minus y over 1 minus e to the power minus y, and this can be rearranged. Remember that we have also used, to reach this we have also used this definition of this z also, because here it contains z, and we put this z and this equation combined and we get this, and this can be rearranged and we get the average number of photons in a mode s, that is equal to beta h cut omega minus 1, and this is our Planck's distribution function that we were looking for. This is our desired Planck's distribution function for average number of photons in a mode. Now we are in a position to calculate various thermodynamic parameters and see how it will work for us. For example, average thermal energy in any mode So this is pretty easy. So average energy is basically average number of photons times the energy of each photon, and in terms of Planck's distribution we can write it as e to the power beta h cut omega minus 1. This is our equation 6. Remember that we need to call this equation 5 previously, so we call this equation 5 and then this is our equation 6. So this will help us later. So now we go on to use the thermodynamic stuff, that is our free energy formulation to calculate the various parameters. So let's go. So again we just go back and write the partition function again for this Planck's distribution. So our partition function, I will write it somehow in a different manner. So we say that this is the function of now k space, and we write it, okay, 1 minus e to the power minus beta h cut omega, which omega is a function of k. And if we now want to calculate free energy, Helmholtz free energy, that is so that we know that can be given as F equals minus 1 over beta log of the partition function, or we can write it as minus k bt log of z. And if now we can write it as, to put the value of z, so we get f equal kbt log of 1 minus e to the power minus beta h cut omega as a function of k. And as we always do, we convert this sum into an integral. We did this several times before, so now f can be written as kbt integral from 0 to infinity the density of states in k space d of k, and log of 1 minus e to the power minus beta h cut omega as a function of k dk. And this basically gives us thermal contribution to the free energy and now we just want to integrate this thing, and before that we should know that this black body radiation has two transverse modes. The transverse electric and transverse magnetic, because electromagnetic radiation. So two modes, and you remember that this theory was based on the standing wave approximation. So we are basically considering standing waves inside the cavity. So now and also d of k is given as d of k is equal to 4 pi k square dk. So if we put the values, so now our f would be, put the values in our equation. Last equation was our equation 8, if we call it this equation 8. So what we get, f equals 2 for the two transverse modes, this initial 2, and then we use the factor v over 2 pi. Okay, sorry, so I should write d of k properly. So d of k actually contains this factor. So d of k is v over 2 pi cubed (4 pi k squared). So this is our d of k. So now I just plug these values in, and 4 pi comes outside, times kBt that we had already, and this is now 0 to infinity k square times log of 1 minus e to the power minus h cut omega over kBt dk, and omega is a function of k. And okay, if we somehow make it clear, omega can be written as ck in the proper form, because we are now doing integration over k. So omega we can write as ck here in this form. So what we gonna get, so we get v over pi squared times kBt, the simplified form k square log of 1 minus e to the power h cut ck over kBt dk. And now we can integrate it by parts. Taking k square our first function, and this log s our second function. So we get f equals kBt v over pi squared. We get k cube over 3 log of 1 minus e to the power minus h cut ck, not kb, just k, and divided by kBt, limits 0 to infinity, minus minus 0 to infinity k cube over 3 1 over e to the power h cut ck over kBt minus 1 times e to the power h cut ck over kBt times h cut c over kBt. Now if we put the limits, if we put k is equal to 0, this term becomes 0, and if we put k equals infinity, then this whole term becomes 0, and log of 1 is 0. So for both limits 0 or infinity, this first term goes to 0, so we are left with only the second term. So we have f equals minus h cut c v over 3 pi squared with a minus sign, and 0 to infinity k cube over e to the power h cut ck over kBt minus 1 dk times e to the power h cut ck over kBt. This is the thing that we are left with. And now if we do some change of variables, so we do the change of variables like this. Let z equals h cut ck over kBt, then we can write it as k cube will be equal to kBt over c h cut raised to the power 3 times d cube, and also the dk will be equal to kBt over h cut c times dz. So our free energy will be written as h cut cv times kBt over c h cut raised to the power 4, the limit of 0 to infinity c cube over e to the power z minus 1 dc. So the integral here is a standard one, and we have a solution for this as pi 4 over 15. So when we put it in, so we get the final form of our free energy as F equals minus C V over 45 kb to the power 4. Okay, so if I remove C from here, so it is C cube below, and then D4 h cut cube pi square. So this is the final form of our free energy, and from free energy we can actually calculate the entropy and the total energy. So our entropy would be entropy of the Planck's distribution, or entropy due to Planck's distribution, that is partial F over partial T at a constant V. So that we will get 4 pi squared kb4 T cubed times V over 45 h cut C h cut cube C cubed. And now it's time to calculate the total energy. that will be equal to E equals free energy plus the term Ts, and we have all of these. So when we put it in, so that is minus pi square kb4 t4 over 45 h cube c cube plus 4 times pi squared kb4 t4 over 45 h cut cube c cube. We get energy equal to pi square kb4 t4 times v at 15 h cut cube c cube. So this is the energy of our energy of the black body radiation inside the cavity, and if we now convert it into energy density or an energy per unit volume, we get so I write it as small e, that is E over V, that would be equal to pi square kb4 over 15 h cut cube c cube times t to the power 4. So we can clearly see that our energy is depending on the fourth power of the temperature. This fourth power dependence is called Stephan-Boltzmann's law. This is known as the Stephan-Boltzmann's law of thermal radiation. So now let's define spectral density. Spectral density we call this U sub omega. This basically gives the energy per unit volume. Per unit frequency. And roughly it can be given as in form of energy per unit volume, that is E, that is equal to E over V. So we can write it as some integral over 0 to infinity U of omega T omega. We call this our next equation, equation 9. And now if you remember equation 6 that we already defined, so we had energy as a function of omega, average energy as a function of omega, that we had like this form. And now if we want to determine total energy, what we need to do is we have to sum over all frequencies. So total energy in this case will be sum omega sum of all frequencies h cut omega over e to the power beta h cut omega minus 1. So now you have a task. Your assignment is, I call this equation 10. Assignment is, you need to use equation 10 convert it into an integral using the density of states function in frequency domain that is d of omega and obtain a result of this shape h cut v over pi square c cubed omega cubed e to the power beta h cut omega minus 1 t of omega. I call this equation 11. So that you need to derive using this method that I mentioned. And then when you are done with this, now I am comparing equation 10 and 11 I get the actual spectral density function, that is h cut over pi square c cubed omega cubed over e to the power beta h cut omega minus 1. This is the spectral density function. And another thing that you need to do is to plot. This is another second part of assignment. Part B is plot u of omega versus beta h cut omega and show me the curve that you got. By the way, this spectral density function, I should call this equation 12. This is our Planck's So region 12 is the Planck's radiation law. So when we will plot it against h cut beta h cut omega, so it will give us a distribution of energy versus frequencies. So that is it. I hope you have learned something about these Planck radiation law. We actually did several things. So we initially discovered the historical perspective, and we got to know that the equipartition theorem of classical statistical mechanics was not enough to explain the thermal radiation behavior, especially for higher frequencies, and Planck corrected it by assuming that Blackbody, the cavity that actually contains a lot of frequency modes, infinite number of modes, and each mode contains discrete number of energy packets or photons, and based on these photons and these levels, we could create our partition function and several thermal properties with this, and we got to know about Stefan Boltzmann's law and the Planck's radiation law from that. We talk next time about the lattice vibrations in a crystal, that is the phonons, and actually Planck's radiation law is also suitable, or we can also use Planck's law, radiation law, to calculate the phonons and their thermal properties in a crystal. So till then, ciao.